Looks like, welcome everyone. This is Musa Al-hassy's PhD oral defense, and I'm the chair of this this defense. My name is Matt Valeriot, and we have the committee members are present, and I'll introduce you to them. You can see their names, but just let me go down the list. Dr. Winter, he's the external examiner. Doctors Farmer and Sakarensky are members of the committee, and the co-supervisors are Dr. Corrett and Dr. Call. So during, what will happen next is Musa will give a presentation of his work of roughly 15 minutes, maybe at most 20. And then there'll be questioning from the committee members. During this time, audience members will be muted and videos off. There will be an opportunity to ask questions at the very end, and so we'll deal with that at the time as needed. Good. So I think we're ready to start. Musa, are you ready to begin your presentation?
Yep, I'm all good to go.
Good. So again, just to reinforce that the guidelines suggest it should be a 15-minute talk, more or less, no more than 20 minutes. We good?
Yep, that sounds great.
Great. Well, thank you. So I'll let you have the floor.
All righty then. Welcome everyone to my PhD defense on do-it-yourself module systems, extending dependently typed languages to implement module system features in the core language. So let's get started. What's the problem? Well, first, what are you going to get from listening to me talk for the next 15 to 20 minutes? Well, first off, you'll see that there's a uniform syntax for record types and term types. Don't worry if you don't know what that means. We'll get to it in time. We'll solve something called the unbundling problem. And we'll see that we can mechanically generate useful data structures for programming by using mathematical theories, right? In particular, you'll see things such as pointed sets give us unit types, or lists arising from collections. So a lot of fun stuff to get to see, hopefully. Of course, before we can actually talk about modules, it's good to make sure everyone's on the same page. What is a module, right? So a module is essentially just a tuple of names. As you can see right here on the left-hand side, we have some names. And for each of these names, we have an associated type on the right-hand side. And of course, all of these are separated by a colon, right? This module is named Monoid 2, and it starts with the keyword record. And we use the word field to separate some of the declarations as parameters and the rest as elements. So in case you're thinking of generics or type classes, and then these would be the struct elements, okay? And we'll be using Monoid as our main example, since whenever you have two things and you wanna compose them to get a third, or smash them together to get a third, you probably have a Monoid, okay? So the problem is, people like to work with monoids at various levels of exposure. They like to say things like, let M be a monoid, or they say, given a monoid over N, the natural numbers. Other people like to say, consider the monoid N with addition. And yet others say, consider the monoid N with plus and zero. So this begs the question, what is a monoid, right? So we can think of a monoid as a type, right? This is just a type. That's all it is. And this type consists of a number of features, right? What you have and how to compose them, etc. But for the other use case, we might think monoid is a type former, right? That once you give it a carrier type, only then do you have another type, right? So you say it's a monoid over a given carrier. That is to say a type class or generics, right? But for the other use case, we would say, no, you have a monoid requires a carrier and an operation, and only when we have those can we define a monoid. Right? And yet again, we might bring other things to the parameter level, right? So notice that the effort here is quadratic. The total number of declarations we have is really, the total number of lines we have is the number of declarations times the number of variations. We'll see that our tool allows us to make this into a linear count, right? So the problem that we're really trying to solve is that structures are meaninglessly parameterized from a mathematical perspective, right? That is to say, there are structures that we would like to use from different perspectives And we want to do so in an efficient and practical fashion without duplicating anything. Right? This is the problem we're solving. It's known as the unbundling problem. Right? So this problem occurs mostly in dependently typed languages such as Agda, but it also occurs in non-dependently typed languages such as Haskell, as we will come to see. Right? So when you're lifting fields to parameters and you're shuffling things up and down, there are a few problems that arise. For instance, we said earlier that Monoid 0 was just a record type, whereas Monoid 1 was a type class or a generic. But their relationship is that Monoid 0 is just the packing away of the carrier for Monoid 1. Conversely, Monoid 1 is just Monoid 0 with an identity constraint. And these relationships can be generated mechanically with our tool, right? Of course, there's a variety of other constructions that are only presented naturally with different degrees of exposure or unbundling. For instance, when people talk about term types, they may say lists are the free monoid over a given data type, right? And they may say, for example, a semigroup is a monoid with a unit with an extra feature. For exclusions, they may say things like a semigroup is a non-unital monoid. And finally, more interestingly, they may say a monoid is a unital magma along with a semigroup such that they share the same carrier and the same operation. Right? So it seems that what needs to be exposed or hidden depends on a case-by-case basis. And rather than insisting on a particular scheme, we say, you know what, don't expose anything and unbundle as you see fit, right? As a position of reference, the audience is welcome to think of JSON objects. JavaScript objects are just malleable key value pairs, right? Because of their malleability, they're a good point of reference, right? They can be used as record types via prototyping. And finally, JavaScript objects are constantly being serialized between different applications, right? So it's a good point of reference to think of JavaScript objects in the upcoming slides. Okay, so let's begin with the first approach, right? Package former. So we have this nice little framework, an editor extension for Agda's main interactive development environment, and it goes out of its way to be super user-friendly. It has syntactic coloring, as you can see. It folds these annotations away. It has tooltips, nice error reporting, in-tool documentation. It's really the bee's knees, right? It's just a delight. So good that we wrote a paper about it, right? Which then subsequently influenced Agda's standard library. As you can see right here in the left side, these are the variations on monoid we mentioned earlier. And if you look right here on the right side, package former has its own definition, a unique definition of what a monoid is. So let's take a closer look at that. So here, this looks almost exactly the same definition we saw earlier. The main difference is now we're going to use the word package former instead of the word record. So this is very similar to when people say, I have a type former. You know, I have lists of integers, lists of characters. List is a type former. And here we have a package former. It makes packages. And notice we also got rid of the field keyword. Otherwise, everything else is the same, right? So if we want the previous variations on monoid, we simply request them, right? So for instance, we say, hey, package former monoid P, please make yourself into an Agda recognizable record. And that's what we do in this declaration, right? And now that we made this monoid 0, we can say, hey, monoid 0, you're a package former, please lift your waist up to 1, right? The keyword waist here just puts the word field at position 1. Likewise, waist 3 puts the keyword field at position 3, right? And of course, we can also form these in various other ways, right? This tool also gives us different capabilities. For example, when you want to talk about monoidal terms, you want to describe them, you want to optimize them, you want to metaprogram with them, you simply request them, right? You say, hey, monoid P, please make yourself into a term type with variables, right? Being the carrier, right? So the carrier is now the term type, please. And you get this nice little data type. So that's really handy. And notice that this is a linear effort in the number of variations. Before, for each variation, we had to duplicate the number of declarations. So we had to multiply it. But now we just write out the declarations once, and every time we want a variation, we just request it. We request it, and we just keep requesting. So it's linear, right? Now, some people might ask, what is this record? What is this waste, right? So this record is a user-defined package transformer, and it's defined as an example in the tool's manual, right? The framework is built around these meta primitives, right? Such as kind right here, or alter elements, or this one right here, waste. So it's built around them. We have these meta primitives, and we have 5 of them, right? Including this compositional forward operator. So let's take a closer look at that. Besides the meta primitives, we also have this variational domain-specific language, V for variational, and it allows users to use Lisp to extend the framework. So we have the 5 meta primitives, such as alter elements, and we give users this variational approach, and they can define whatever they like, such as this union pushout construction, right? Now, to show that the meta primitives are actually deserving of that name, that status, the framework goes out of its way to derive a number of common ones, such as these, right? For example, we have an extended by variational, we have a renaming one, we have a union one. So we have a bunch of these, right? To show that, hey, these primitives really are good enough to derive a host of other ways to manipulate packages, right? And notice on this slide, each line is a specification of a theory that we would like to use. There are 200 terse, readable specifications of things we actually want to write, right? And they elaborate into about 1,500 lines of type-checked Agda that we actually want to use. So to say the least, this package former is a very useful engineering result, right? From package former, we learned 3 useful lessons. That there's really no difference between fields and parameters. It's an illusion, like input and output in Prolog. We realized that contexts or name type tuples can be thought of as record types, type classes, but they can also be interpreted as term types. And finally, we realized we can make a framework that is efficient and expressive and finally extendable. But can we lift it from the status of an editor extension to an in-language library? And that's the next section. The answer, of course, is yes, we can. Right. So recall we talked about monoids, and monoids let you compose things. How do you compose natural numbers? Do you add 2 numbers or do you multiply? Haskell's solution is to duplicate numbers using new types because instance resolution requires unique instances for type class parameters, right? So it makes a duplicate such as sum, and it makes a wrapper such as product, and says sums are additive and products are multiplicative. But we think there's an alternative approach. In particular, encouraged by the prototype, we think start with fully bundled and then expose fields on the fly. Again, following the prototype as the guide, we would do this with metaprogramming. Unfortunately, the current mechanism for Agda is too weak to touch records directly. But every record is a so-called sigma type. So rather than using this beautiful, syntactic sugar, the word record, and then set and where and field, rather than having all of this delicious, beautiful eye candy, we go to this. We use a raw form. All right? We have pies everywhere. We have lambdas everywhere. We have sigmas. And I think this is equally pretty, but some of you might think this is hurtful on the eyes and hurtful to the soul. You might think it would be nice to have a prettier notation where later elements, such as this one, mention things that appear in earlier positions. But later things, depending on earlier things, that's the insight of monadic do notation, right? And that's how we can implement that. So we decide to use these things called contexts, which are just exposure indexed types, right? And this is the shocker of it all. This is the bind definition that allows us to use do notation. And it's really small. It's so small, I can show it to you right here. And this is where the do it yourself in the title comes from. When we're looking at the exposure and it's 0, we decide to make a sigma type. But when it's non-zero, then we decide to make a pi type. Users are allowed to change these however they want using different different grouping mechanisms. This is the do-it-yourself, and it's so small and easy to alter. We think this is pretty nifty. So let's actually try to use these. So if we have this context, right, it's a module, right? How do we treat it as if it was a generic or type class, right? Well, a context is just an exposure index type. So let's try to give it an exposure level. We give it an exposure level of 1. Okay, we'd like now to apply this type class, this generic. We'd like to apply it to, say, the natural numbers, and we try to do that, and we get a type error, right? It's exposure indexed. We gave it an exposure, but this is a set. This is a type. We need a function on types, not a type of functions. So what we need is a combinator, and this combinator just swaps pi's for lambdas. As the name of this combinator suggests, right? It takes a type of functions and turns it into a function on types, right? For convenience, let's also introduce a mixed notation, right? So perhaps this is a bit airy. Let's look at it more concretely. Here's our beloved monoid yet again. If we decide to make it a waist 0, then we'll get a nice record as we had before. If we decide to go waist 1, we'll get a type class. We have a single argument. If we decide to go to waist 2, now we have our record back here, and now we have 2 arguments out there, right? So this solves that additive or multiplicative problem that Haskell decides to solve using duplicate new types. So that's really neat. And of course, just as you can form these types really easily, you can introduce values in a familiar notation. Here's our monoid. We make it a waist 1 to get a type class or a generic. We instantiate it at the natural numbers, and then we make a value just by a familiar, lovely old tuple, right? So in summary, you can unbundle module fields as if they were parameters on the fly, right? If you have a module such as this, you can just unbundle whenever you like. Unbundling at 0 gives you a record, whereas unbundling at 1, for example, gives you a type class, right? Which you can apply and then make values of. So that's really neat. Now, what if you wanted to serialize this, right, to get the descriptive syntax? Well, apparently, we can do that too. Starting with our familiar monoid, we can massage this into a fixed point of a type former, which we can then package up as an agda macro. Right? Let's look at this in practice. Right? So here's our lovely monoid again, nothing new. Right? If we ask for this monoid, we make it into a type class, and then we ask for it to be a term type. What happens is that we only keep the sources of the symbols that target the argument carrier, right? And of course, working with fixed points can be a bit daunting. So we can introduce some prettifications, such as empty and branch, to hide these fixed point values. And with these useful names, it suddenly becomes not too difficult to see that this is a familiar data type, that it's a form of binary trees, right? And we see this by doing nothing. We just send empty to empty and branch to branch, right? That is to say, algebraic data types are also terms, right? You have a module and you wish you had the associated descriptive syntax, you simply request it and make some patterns for it. So that's really neat. And of course, as we mentioned earlier, lots of data structures from programming arise this way as well. So that's really cool. In conclusion, right, I want to if there's anything you're going to take away from this talk, I hope that it's just from these name type pairs, the single source of truth, we can derive a lot of related things, right? Like these ones. And these are useful, practical, and ubiquitous. They appear quite often, right? And you usually want to have them. And it's neat that we get them from a single source of truth. I think that's pretty cool. All right. And I'd like to just point out that, you know, our contributions are, we were able to identify module design patterns that are actually used in the wild. We brought algebraic data types into the fold of grouping mechanisms. We can mechanically generate term types used by programmers from theories that mathematicians are interested in. And we have a practical implementation for all of this. And it's mostly type theory agnostic. So that's really cool. Thank you for your time, everyone.
Thank you, Musa. Yes, that's don't know where the button is to applaud, so I'll just do it this way. But, thank you.
Thank you.
Great. So now